we go. Okay. Thanks. Yeah. So electronegativity refers to how tightly atoms want to hold on to electrons. And again, I'm going to stop iterating this, but we're really talking about valence electrons because we don't care about anything that's in lower energy shells. So hold on to electrons. Okay. And so if you are you have two atoms in a bond, the one that's more electronegative is going to sort of win that tug of war for the electrons. And it's not to say it takes them all, but it has a larger distribution of the electrons that are in the bond. And so we want to know how electronegative each element is. And there's a useful mnemonic for this, which is, I'll write it out. So flunk the bishop, C. Okay. So fluorine, oxygen, nitrogen, chlorine, bromine, iodine, sulfur, carbon, hydrogen, phosphorus, and silicon. Okay. So fluorine's the most electronegative, and then as you work through, you go down in electronegativity. And there are numbers, there are different electronegativity scales that one can use to quantify these, but really we just care about sort of the relative order of electronegativity. It's not critical to know any of the actual sort of quantitative assessments of that property. So what does this mean? So it means that when I have a covalent bond and I've got two atoms of different electronegativity, that bond is unevenly distributed. And so a good example is methanol, okay? And we know that from, we know that oxygen is one of the most electronegative elements. And carbon is pretty sort of neutral. Okay, and so if I were to just sketch out qualitatively the nature of the sigma bond between carbon and oxygen, if I were to draw the orbitals, it would look something like this. And I'm gonna exaggerate it to make the point, but okay, so this kind of bubble represents the bonding orbital. And you can see that it's bigger at oxygen, okay? And I just want to make myself a note because I want to send you guys some pictures after class. It's bigger at oxygen. So what we say is that the CO bonding orbital is polarized towards oxygen. I've got more electron density at any given instant around oxygen. And so that generates what we refer to as a bond dipole. And it arises because of this discrepancy in the electron distribution. So the oxygen has more negative charge and the carbon is more positively charged. And it's not to say there's a full charge, certainly that's not the case, but there's what we call a partial charge. And so there are different ways of sort of representing this. One way is with this arrow, where we sort of put the positive, embed kind of a positive sign. You can also write sort of like delta minus, delta plus at the oxygen and carbon atoms. And so these dipoles are very important. When we get to intermolecular forces, they'll come into play. There's a simple mathematical definition, which is we can describe the dipole as mu, and that is equal to Q times R, where Q is the charge, the partial charge, and R is the distance. So intuitively, hopefully that makes sense. You know, as you increase the charge or you increase the distance between the atoms, you have a bigger molecular or bigger dipole within that bond. Okay.
And what is mu representing again?
Mu is just kind of the abbreviation for dipole. Yeah.
Okay.
Yeah. So, all right. So I want to briefly cover Vscpr theory. Hopefully they talked about this in general chemistry, but I'll just mention it here because we're going to use this model. So this is the valence shell electron repulsion theory. So Vscpr. And okay. It's a very complicated way of saying atoms want to distribute themselves in space as much as possible. Okay. They want to socially distance. That's a bad joke, I know, but it's just so obvious. Yeah, so they just want to be apart from each other, okay? So what that means is we can use that then to think about, that then determines the geometries of molecules with respect to specific centers. And so I'm going to draw methane again, and that is the line drawing of methane in 3 dimensions. And so remember, I mentioned that the wedge means the bond's coming out at us, and the hash means it's going into the plane of the paper, and the other 2 are in plane. And so it's a general fact, when you have 4 ligands attached to a single atom, 4 other atoms attached to a single atom, the way that those can get furthest from each other is to occupy a tetrahedral arrangement. And that's what we see here. So I can sort of sketch, I can overlay, you know, a tetrahedron, and hopefully, you know, you can see it in there. Basically, we put the hydrogen atoms at the corner of the tetrahedron, and there's a very specific bond angle then that derives from this arrangement, and that is about 109.5 degrees, okay? So if you sort of have HCH bond angles and you set them at 109.5, that maximizes the distance of any hydrogen with respect to another. And so this is for 4 ligands. For 3 ligands, the situation is a little bit different. I could stick with my 109.5, but I can actually do a little bit better. And the way I can do better is if I planarize the molecule. And so an example would be boron trifluoride. And so now we've got 3 fluorines around boron. And if I put these in plane, I can set up a bond angle then of 120 degrees, okay? And so that's a little bit bigger. So what we find is that we get a nice planar arrangement, trigonal planar arrangement of atoms when you have 3 ligands around a specific atom. And then going down to 2, it should be hopefully intuitive. This is acetonitrile. It's a very common solvent in organic chemistry, actually. And if we think about the carbon here, okay, forget about the bonds for a second. Don't let that throw you off. I've got two ligands on carbon, okay? And so the best way to get them apart from each other is to have them 180 degrees, separated by 180 degrees, okay? So, we can use the Vscpr theory to basically fall back on or understand or predict the geometry of molecules. And so again, I want to sort of emphasize a point, which is like, consider the number of ligands. And by ligands, I mean attached atoms, atoms that are attached to the atom of interest. Consider the number of ligands rather than the bonding, then double bond, triple bond. You don't need to sort of think about it from that perspective. Just consider how many things are around an atom. Okay. And so, okay, so going on then, I want to get to something that's a little more sort of nuanced, which is this idea of a resonant structure. Okay. And so I said to you guys that, there's just a couple concepts that we got to get here, right? Hyperconjugation, resonance, and inductive effects. And so here's one of them. And we're going to introduce it, and it's going to come up, and we're going to refine our understanding of it as we go through the course. But the essential point is that or the utility of resonance structures are to sort of more accurately describe the bonding in a molecule than a Lewis dot or a line structure. Okay, and so this is best illustrated with an example, and we'll use this molecule, acetate. And so let me draw it in there. So this is acetate. Okay, and so acetate is the conjugate base of acetic acid. Acetic acid is found in vinegar. It's a mildly acidic species. Anyway, I can draw this out, and the way I've drawn it, it might actually appear to you that the two oxygen atoms are different, right? One has a single bond to carbon, and the other has a double bond, right? And in fact, if one were to go and measure, you can measure experimentally the lengths of these bonds, we find that they are identical. So those CO bonds experimentally are 1.26 angstroms, okay? So how can that be? So I've got a single bond to one oxygen and a double bond to another. How can they have the same bond lengths? We know that as you increase sort of the number of bonds between atoms, they get tighter and tighter together. And the answer is that that's not really the case. You don't have a single and a double. In fact, you have kind of something that's somewhere in between for both atoms, both oxygens, and we can show that with our resonant structure. So what I'm going to do, and I'll just redraw it here for clarity, is start with a pair of electrons on the oxygen that is formally negatively charged. And I'm going to use an arrow to push those electrons down to carbon, okay? If I were to stop there, I'd have a problem. And the problem would be that I'm surrounding my carbon with 10 electrons, okay? And we can't do that. That violates the octet rule. And so what I need to do instead is break a bond. And the bond I'm going to break is one of these CO bonds. And so so I get to there, okay? And so couple comments about sort of nomenclature here. So I've used a special arrow between these resonance structures. This is a double-headed arrow, always used for resonance structures. And so that double-headed arrow has a very specific meaning to organic chemists. It means that we're talking about resonance structures. We don't use it for chemical reactions. We don't use it for equilibria. We have different arrows for that. So keep that in mind. And then the second thing is that I put brackets around, and that's sort of more subjective. Most people, I think, do that. Sometimes you'll see resonance structures without the brackets, but the brackets are really to sort of suggest an important point, which is that these are the same molecule, okay? They are different representations of the same molecule, okay? Sort of like give you an analogy, if I were, if we're sitting here on Zoom and I sit here like this, right? And then I sit here like this, and you look at both sides of my face, right? You wouldn't think there were two of me, right? Hopefully not, but it's the same, I'm the same person, right? Those two images contribute to a single entity. In that case, me. Here, these two pictures of acetate contribute to a single entity. They contribute to the structure of acetate, okay? And so based on that, we can nail down some specific sort of comments about resonance structures. So the single most important thing is that the real structure of the molecule is composition of individual resonance structures. And I apologize, I'm abbreviating on the whiteboard because this is very slow to write on. So if anything's unclear, you can chat box it or just, shout out. Okay, so any molecule, each molecule is a composition of its individual resonance structures. And any given molecule is more stable, and this is sort of less important, but good to know, is more stable than the individual resonance structures. Again, so because you're kind of looking at one snapshot or another, you're not really taking the whole thing into consideration. And the energy of the overall molecule is actually lower than what you would get by just considering those specific structures. And where it gets very interesting and very useful, so acetate's kind of a simple example because of the symmetry. But when you have molecules that lack that type of symmetry, it gets more nuanced. And so let me give you another example. So okay, so this is, this is sort of N,N-dimethyl methanaminium. It's also known as the Vilsmeier reagent. We use it a lot in organic chemistry. And I've got a double bond between nitrogen and carbon, okay? What I can do is I can start to think about resonance structures for this molecule, all right? And the first one I'm gonna draw is I'm gonna take one of the bonds in the double bond and push those electrons up to nitrogen, okay? So drawing a resonance structure, double-headed arrow, push the electrons up. I'm left with a single bond. Oops, sorry. Okay, I need to keep track of the electrons. And so the two that were in this bond are moving up to nitrogen. So I got a lone pair now, okay? And I told you would meet Larry. There he is. Larry, not now. All right. And the two that were on carbon now are gone, right? And if you assign formal charges, and I'm not going to do this here, but I'd encourage you to convince yourself that the carbon now has the positive charge, okay? And so that's another resonance structure. I can also do something else. And so let me do this. And this is a very unimportant resonance structure, but I'm going to draw it to make a point. So I could go the other way with the electrons, okay? And so we'll call this A and then B. Okay, and again, please work through this and convince yourself that you can follow the charges that I'm drawing, but I've now got a negative charge on carbon and 2+ on nitrogen, okay? Okay, and so this resonance structure we actually don't even consider, okay? And the reason is for the following sort of guidelines that I'm going to give you. So the first thing is that the best resonance structures, the ones that are the biggest contributors to the overall structure of the molecule, are the ones that satisfy the octet. Okay, and in this case, I can go around and count electrons, okay? And if I assign a letter to the structures, it is structure A that has an octet around both carbon and nitrogen, okay? The second criteria is that we want to minimize overall charge. Okay, and we'll call this one on the bottom here C. We can see that in structure C, I've got 3 charges, right? I've got 2+, 1-. I've maximized overall charge, right? And so C is absolutely the worst. Okay, A and B, one on the right there, are sort of comparable in their sort of charges. The third thing is that you want to minimize, put negative charges on electronegative atoms and positive charges on electropositive. And so I'll just use this kind of to mean electropositive or non-electronegative. Okay, so those are the 3 criteria. One is the most important. It's the thing that carries the most weight. Okay, 2 then follows, and then 3 is kind of the final consideration if you're really trying to get in there and parse structures. And so important point is that you can see that kind of criteria 1 and 3 are sort of in opposition here, because if I look at the structures with respect to criteria 1, A looks the best. But if I think about criteria 3, B actually looks better because carbon's less electronegative than nitrogen, and that has the positive charge. And so that's where you kind of have to apply a little bit of a filter and say, okay, well, it's definitely an apparent contradiction, but we know that it's more important to have those octets filled, okay? And so what this leads to is a overall picture of the molecule that, again, this is, I'm just gonna put some arbitrary numbers for discussion, not meant to be taken literally, but we'd say maybe, you know, the molecule is, you know, is something like, you know, looks like 70% A, maybe 25% B, and 5% C, okay? So these are sort of weighted contributions to the overall structure. And I'll say it one more time. I'm talking about one molecule, okay? This is not to say I've got an equilibrium with 70% A and 25% B and 5% C. Not the case, not the case. I've got one molecule and it looks a lot like A, a little bit like B, and even less like C, okay? And what we're really trying to do here is just have a way to communicate sort of the fuzziness of these structures, the fact that, you know, charges aren't all in one place, bonds aren't always 2 and 0 or 2 and 1 and 3. You know, there are lots of intermediate sort of circumstances, and that's what we're trying to get across with the resonance structures, okay? All right. All right, so I'm going to go on to a little bit of quantum mechanics, and we kind of like put our feet in this in the last lecture, and I'd like to just do a little bit more systematically because, again, we're not going to use this throughout the semester, but it's good to put us on the right footing here. So, and for those of you that are chem majors, you will go on and take a whole semester of quantum, which is, it'll blow your mind, okay? And for those of you that aren't, hopefully you get enough of a foundation here that you can understand where a lot of, you know, sort of the theory comes from. So quantum states that electrons are described by what we call a wave function. A wave function, and we typically abbreviate that like that. And the wave function is basically this idea that, you know, what the wave function gives you is the probability of finding an electron at any given point at any instant. So okay. And when I say point in space, you know, you can write wave functions for, you know, space in your dorm room and, you know, finding an electron anywhere. But we're concerned with space around an atom, around a nucleus, okay? And the wave function is described by what we call quantum numbers. So okay, and so there are a couple that you need to know about. And so one is what we call the principal quantum number. So okay, and that is abbreviated N, and that can take the values, just whole integer values, so 1, 2, 3, etc. Okay. The second one, and again, I expect that, you know, if you haven't seen this, this is probably like, what is he talking about? But I'm going to connect it with orbitals in a second, and so just hang in there. The second quantum number that we need to worry about is what's called the angular momentum quantum number. And that is abbreviated L, okay? And that can take the values of 0 to n minus 1. So it depends on the principal quantum number, okay? And L is described in turn, well, when it has specific integral values, we assign specific letters to L. So for L equals 0, we can abbreviate that S. And for L equals 1, we call that P. So hopefully you can see where this might be going. And for L equals 2, we call that D, okay? There's also what's known as the magnetic quantum number. And that's abbreviated M sub L, and that goes from 0 to plus minus L. So if I have, for example, principal quantum number of 1, okay, then L is defined as 0 to n minus 1, and so it's just going to be 0. Okay, and M sub L is defined as 0 to plus minus L, and so that is also 0. Okay, and so this, I'll show you, is what we call a 1s orbital. Okay, now if I go to the principal quantum number of 2, n equals 2, now I can have two values of L. So L can go from 0 to 1. Okay. And for L equals 0, M sub L still equals 0. For L equals 1, M sub L equals minus 1, 0, plus 1. Okay. And so these are what we call 2p orbitals. And n equals 2, L equals 0, M sub L equals 0 are what we call 2s, a 2s orbital. Okay. And so essentially what we're trying to do here is sort of show you in the simplest possible terms where atomic orbitals come from. Okay. And so let me just sort of do a recap. You have this wave function. This wave function has different terms, N, L, M sub L. Okay. L and M sub L are dependent upon N itself. Okay. And N can take the integral values going 1, 2, 3, 4, 5, etc. Okay. And so that principal quantum number defines what orbitals sort of are described by this wave function, okay? And again, if this is confusing, we can talk about it in any time. You don't really need to you don't really need to know this that sort of rigorously for organic, which is great. You just need to know that when we draw these orbitals, there's a sound quantum molecular basis for drawing them, okay? And so, so what do these orbitals look like? So the 1s orbital is a spherical orbital. So it's a spherical orbital, very easy to draw. N equals 1, L equals 0, okay? The 2s orbital is where things start to get a little bit esoteric. And so the 2s orbital, and there's nice sort of colored images of this in your text. But the 2s orbital is where you have, it's still a sphere, but you have what we call a node, okay? And okay, it's like those nesting dolls. It's like a sphere inside of a sphere, right? Except it's kind of hovering inside of the little sphere is hovering inside of the bigger sphere. And the point is that at the surface of that smaller sphere, there's what we call a node. A node is a point or surface of 0 electron density, okay? And the sign of the wave function changes as you pass through that node. So I can draw it like that. So minus on the outside, plus on the inside. You can draw it the other way, minus on the inside, plus out. That how you choose the signs is arbitrary. Nature doesn't really know plus from minus. And again, this probably seems strange. There's a good image of this in the text that hopefully will help you. And so we know that for n equals 2, we get to this n equals 2, L equals 0, we get to this spherical orbital. But we said that when n equals 2, we can also have L equal 1, which leads to these m sub L's of -1, 0, and +1. And that is where we get to our 2p orbitals, okay? And so n equals 2, L equals 1, m sub L equals -1, 0, +1. And the 2p orbitals are like dumbbells, okay? And so again, putting them out on an axis,
Professor, I have a question.
yeah, go ahead.
So you mentioned that like it moves as like a wave function, but I like don't really understand like how it does that within like a spherical area.
Yeah. So the wave function. So think about like a function in 2Ds, in 2 dimensions, right? So like if you have a 2-dimensional plot, right? I can describe a point on that plot by any sort of by a function, right? And we're going to do that in 3 dimensions, okay? So the wave function tells me rather than sort of defining different points, it defines the probability or the chance of finding an electron at that specific point, okay? And so, for example, if I had the 1s orbital and it's a sphere, and I wanted to, look right here in chemical space, I wanted to know, what's the probability of finding an electron there? The wave function would tell me that, okay? Does that make sense?
A little bit. So then,
A little bit, yeah.
where there's a node, is the node just like a single point where there is just like there's like zero chance of there being an electron there?
Yeah, nodes, in this case, the node is a plane, a spherical plane, okay? Nodes can be points, they can be sort of two-dimensional planes, they can also be spheres, okay? And yeah, regardless of the shape of a node, they all have the same property, which is that if you were to ask the wave function, what's the probability of finding an electron at that point in the node, be it a point on a spherical plane or 2D plane or a point, it would be 0. Yeah.
Okay.
Yeah.
And then sorry, last question. But for like the 2p, I guess like molecules, is it the little dumbbell? Do they have the dumbbell shape and the spheres? Or is it like once it's in the 2p, it's like just the dumbbells?
No. So when we get to, for everything except hydrogen, because hydrogen is just kind of 1s, right? As soon as you get to the second row, carbon, oxygen, nitrogen, okay? We've got both, we have the 1s orbital, but then we also have the 2s, and then overlaid on top of that, we have these 2p orbitals.
Okay, great, thank
Okay.
you.
Yeah. And so, all right, so trying to keep track of everything here. All right, so we have our 2p orbitals and they're dumbbell shaped, okay? And they also have a node. In this case, it's right at the center. And when we pass through that node, the sign of the wave function changes, okay? And so I just wanna say one more thing before I go on, which is, might be obvious to many of you, it may not be apparent. What is he drawing with these nodes? Why is he drawing dumbbells and spheres, right? I'm drawing dumbbells and spheres because the dumbbells and spheres represent the boundary of the wave function within which there's a 90% probability of finding the electron, okay? So okay, so basically I can draw a dumbbell, and what that dumbbell tells me is that the wave function sort of underlying that, if I were to sort of calculate the electron density or the probability of finding an electron, 90% of the time it'd be within that region bound by the dumbbell, okay? And so it's just a nice way to sort of qualitatively say, hey, look, this is where the electron probably is. It's probably within this dumbbell or this sphere somewhere. Now it can go other places. It can end up outside of that, but those probabilities are very low. And so we're not going to really worry about it. Okay. We're just going to kind of make this approximation. And that's helpful because it allows us, if you were to sort of have to consider 98% or 99 or 100% probability of where the electron would be, it would be just intractable to even really think about it. So these are the 5 orbitals that you just kind of need to get comfortable with for the entire class. We're not really going to get into like n equals 3. You might see a little bit of it. Certainly if you take inorganic, you'll probably see it. But for organic chemistry, we're really concerned about the 1s orbital, the 2s orbital, and the 2p orbital, okay? And what we can do then is basically look at these orbitals as essentially orbitals are, one way to think about orbitals is that they are states that are available to an electron, okay? Okay, again, you could think about it like this. You know, if you were to walk into a classroom and there were 10 seats, right? Or maybe let's just say 5 seats. Those seats are available to you. You can go and sit in them, right? That's what an orbital is for an electron. It's like a seat that it can sit in, okay? The difference is that whereas the seats in, you know, in a classroom might be identical, these orbitals are different, okay? And the difference is really the energy of the orbitals. Okay, and so if I were to sort of list them, the energy of those orbitals increases as you go through the series 1s, 2s, 2p, okay? And so, you know, it's as if the 1s orbital is the lazy boy recliner, the 2s orbital is kind of the kitchen chair, and the 2p orbitals are the bar stools, right? So if you're an electron, which one are you going to go and sit in? You're going to sit in the one that's most comfortable. You're going to sit in the one that's lowest in energy, okay? And this is a good breaking point. We'll start then, well, I'll start in the virtual lecture with how we fill these orbitals and what that all means and stuff. But yeah, I think this is a good point to stop. So as before, I'll just hang around. Anyone that wants to chat, I'll be here. And if not, I'll see you on Friday, and I'll do my best to get the Friday's lecture uploaded soon. And then Friday during this time, we'll do some problem solving. Okay. So thanks everyone. Hope you had a good week, and yeah, I'll see you in a couple days.
Thank you.
Thank you.
I have a quick question.
Thank you.
Yeah, go ahead.
Thank you.
Are the 3 p orbitals equal in energy, or does it increase like X, Y, Z?
Nope, they are equal in energy. Yeah, it's a good question. Yeah, because again, like nature doesn't really know X from Y from Z. You know what I mean? That's just kind of like an arbitrary reference that we apply, but they're all equal in energy.
Thank you.
Mm-hmm.
Professor Curzon, what causes a node?
The node derives from, I'm not going to be able to give you a good answer. It derives from change in sign of the wave function. So as if you're going, let me redraw the orbital. If you're going, so you have a 2p orbital, and my electron sort of wants to get to the other side, it kind of, the sign of the wave function has to change, and sort of in doing that, you wind up with this spot of kind of 0 probability. Okay.
Okay, but like for the 1s orbitals, like how do you know where that is, or it's just kind of arbitrary?
Oh, 1s, there's no nodes. Sorry.
Oh, so the only ones with nodes are the p orbital, starting with the p orbitals up until the higher ones.
And the 2s. So it's an important point. So 1s is like a perfect sphere, and there's no nodes. You don't need to worry. It's very simple. 2s, you get this node, and it's a weird kind of node because it's like a sphere that sits inside that bigger sphere. Okay. So like if you were imagine like a cross section, let me, yeah, maybe this will help. So let me draw let's think about, okay, so I'm looking at a cross section. So I'm, it's as if I took that 2s orbital like an apple and cut it down the middle, and now we're looking at the inside. If I'm an electron and I'm coming here, right? It's like, this is the plus region, and then I hit that sphere, I can't exist there. I know it's like totally bizarre, but like, you just can't have an electron there. And so there's zero density, yeah.
So the node is the like hole in the center.
The node is,
That is a node. Sorry, is a node, just because it has to do this, is a node like where an electron is more likely to be found, or is that the orbital? Like, yeah, what is it?
yeah, no, so, all right, so let me back up for a second. So, okay, I'm gonna like try and like rebuild the explanation real quick, okay? And we'll start with just like the 1s orbital. So if I draw a 1s orbital, perfect sphere, okay? No nodes, no sign changes. What am I drawing? I'm saying to you, within that sphere, there's a 90% chance of finding the electron. Does that make sense? Okay. Now, if we go to 2s, there's a node, okay? And maybe part of what's challenging is like the nodes take on different shapes. So nodes can be points, nodes can be like a two-dimensional plane, or they can be this sphere. But what that means is, so if I draw the 2s orbital, and this is sort of the outer boundary of the orbital. Okay, so that outer boundary is basically like where I can, it's the same as kind of the 1s. So it's like within that boundary, there's a 90% chance of finding the electron. Okay. But there's a rub, and the rub is this is the node. And so there's this, this sphere inside the sphere where there's just no electron density. Okay. And I can't, if you were to look at the wave function mathematically and ask what the probability is of finding an electron at that inner sphere, it would be 0. But if I progress further inside to like the core, there's probability there. So I can find an electron there. Okay. I don't know.
So basically, like
yeah.
the shell part of it, of the sphere, of the inner sphere, you can't have an electron in, but inside of that you can have an electron.
Yeah, exactly. But just to kind of clarify, so the electron isn't in one place or the other. It isn't in the outer sphere or in the inner sphere. It's all over. What we're talking about is the chances that when you look, you'll find it in one place or another. Okay?
Yeah, so basically there's 0 probability in the like shell part of the inner sphere, but inside the inner sphere there's 50% probability. And
yeah, there's some
outside the inner shell there's 45% probability or something, but in the actual shell part of it there's 0% probability.
Yeah.
Okay.
Exactly. It's like I can't really think of a great physical analogy. You described it perfect. You could think about the shell maybe as like an eggshell. The node is like an eggshell. Like it can be inside of that or it can be outside. It just can't be on that exact shell. Yeah. And so
I'm not sure.
Yeah, go ahead, Dana.
I was just I'm not sure if I missed something, but when you draw the dumbbells and you shade in like 1/2, like what does that mean?
What I'm showing is the change in sign of the wave function. Okay, so basically, you have a certain, there's a certain probability of finding the electron here, right? In sort of this unshaded region, okay?
Mhm.
There's also a probability of finding the electron in the shaded region, okay? But the wave function itself changes sign, okay? And so I don't know if this is really accurate, but it might be a good way to think about it. Is like you could just sort of think about it as like you have a negative probability. So it's, it's 50% on one half and minus 50 on the other, okay? Just as a way to think about it. I don't think that's actually correct. You don't have negative probabilities, obviously, but the sign of the wave function changes, and it's always going to change when you pass through a node, okay?
Okay.
And the electron doesn't care. So the electron is as happy in the shaded as the unshaded region, okay? But the reason this gets to be important is when we start to talk about bonding. Bonds are essentially sums of atomic wave functions, and when you start to add them, the sign matters, because you can intuit that if you have plus and a minus, you get nothing, and then two pluses are good, two minuses add up in the same direction. So that's kind of where the sign comes into play. Yeah, but as far as electrons are concerned, like, it doesn't really mean anything to them.
Okay, and then I was kind of confused as to how the wave function like relates to the actual like physical like boundaries, or like the orbital shapes. Like, is the like actual sign function like describing the motion of the electron, or is it just like I don't really understand how the two like are like related to each other, if that makes sense.
Yeah. It's I think a good way to think about it is like the wave function just gives me a probability, really. I can sort of interrogate the wave function and say, what's the probability that I'll find an electron here or an electron here, anywhere in space. And the wave function gives me that information. So it'll say, okay, you got a 30% here, 2% here. I'm just picking numbers, and so the dumbbell is essentially, or the spheres are essentially, you can imagine the sphere and the dumbbell as saying, okay, I'm going to interrogate the wave function, and wave function, I want you to tell me like where 90% of the density, most of the density, 90% of the density is going to be, 90% chance that the electron is in a given region. Does that make sense? So that's where the shapes, that's the connection between the shapes and the wave function. So the shapes are basically the shapes are a descriptor, or they are a representation of, their graphical representation of the wave function. And what they mean specifically is that there's a 90% chance the electron will occupy the space defined by these shapes. The wave function still gives you non-zero probabilities outside of that space, but they're, in aggregate 10%. And so we just kind of ignore them as a way to sort of focus on, discrete areas of space, if that clarifies.
Okay, all right, thank you so much.
Yeah.
Professor, this question was asked in the chat, and it's also my question. Will the quiz on Friday, meaning next class, cover the information from the recorded lecture on Friday, or is it just Monday, Wednesday?
No. Yeah, so it'll be, this week it'll be Monday, Wednesday.
Okay.
Next week it'll be Friday, Monday, Wednesday. You know what I mean? Yeah. And also it's not, it's a little bit of a misnomer. Oh, she signed off. Yeah, it's not really a quiz. It's just kind of like a study group.
I had a quick question, Professor. If we go to our 2s orbital example, how is our electron going from the, say, a positive sign to a negative sign without crossing the node, that surface?
Yeah, so this is the sort of, crazy wackiness of quantum is like, the electron doesn't move like a classical object through the orbital. The only way that we can describe the electron is with these probabilities. And so if this doesn't make intuitive sense, it doesn't, it's like it just doesn't jive with everyday experience. But basically the best we can do in describing these subatomic particles is say, look, all right, there's a strong chance I'm going to find it here. There's a strong chance I'm going to find it here. There's a 0% chance I'm going to find it at this node. You know what I mean? So it's not, you don't want to think about it as kind of like traversing a landscape. It's more, where's it going to be? Where's it going to be? And the nodes are where it absolutely will not be. I don't know if that helps. Yeah.
Yeah, got it. Thank you.
Yeah.
Professor, can you talk a little more about what you mean by satisfy acetal when we were talking about resonant structure?
Satisfy, what did I say? Satisfy.
I don't know if I took it wrong. Maybe
Yeah.
I just missed it. But.
Minimize. Oh boy, that's sorry.
Yeah, what was
That's an octet. Yeah.
Oh, sorry.
I'm gonna write that in because hopefully that'll get recorded and end up. Yeah, that says satisfy the octet. So 8 electrons around all non-hydrogen atoms.
Thank you.
Yeah.
Thank you very much.
All right. See you Friday.
Yeah,
Bye-bye.
bye.
Yes.